Welcome to HAO Colloquium today. Today we have Dr. Kyle Augustson, and Kyle's a postdoc here, so a familiar face to everyone. Kyle received his triple major bachelor degrees in math, physics, and computer science from Oregon State University. And then came to CU, got a master's degree and then PhD from the Astrophysics and the Planetary Science Department. Then last year, he came to HAO as an ASP postdoc and has been working mainly with Mark Misch. His main research interest is to study the solar and stellar convective dynamo using MHD simulation. And also, I think he's interested in the high performance computing, and you have authored a book
Yes.
as an undergraduate student. Pretty impressive.
All right, thank you, Henley. Okay, so some of you saw a little bit of this talk already, but I'll go through it for those of you that haven't. So today I'll be talking about a particular case. You can kind of think of it along the lines of the Millennium simulation, which was done by Paul Charbonneau and company. Back starting in 2010 or 2009 is probably when they started the simulations. But just to cover a few of the basic aspects of the solar dynamo, at least that we can observe it at its surface. Of course, we have the 11-year sunspot cycle, which maybe corresponds to some sort of magnetic energy cycle. We have the 22-year polarity cycle, wherein the radial field effectively flips its sign every 11 years and returns to its original polarity every 22. We have poleward can everybody hear me? Okay. Okay. We have poleward migration, basically starting from mid-latitudes towards the pole, and we have equatorward migration of these magnetic features. We also have long-term behavior. So here we have the sunspot record stretching back to the early 17th century. Of course, starting with Galileo and company with their sunspot measures. Here are some reconstructed sunspot diagrams from Reed's, Rainer Arlt, and of course the modern sunspot record here. And you can see these features basically have been maintained for at least 4 centuries, where you have this equator migration. Hard to see the poleward migration on this one, but you also have longer terms, so beyond the 11-year and 22-year cycles, you have longer term behavior, something like the Gleisberg cycle, which is basically these envelopes in the peak amplitudes of each magnetic energy cycle or sunspot cycle. You can also see several minimum, of course, like the well-known Maunder minimum, which lasted something like 60 years, wherein you had very few sunspots, only a couple per year typically. And also, at least as far as the observations from the Observatoire de Paris, you have some hemispheric asymmetries. Namely, in this case, you have more sunspots in the southern hemisphere than you do in the northern hemisphere. And of course, since we'll be talking about dynamo models, there are many important ingredients for this. Of course, one is convection, which I won't show here, but also you have differential rotation, and the meridional flow may play a role as well. But it basically highlights a couple of very well-known features of the solar differential rotation. Of course, you have the tachocline, you have a near-surface shear layer, and relatively conical profile for the differential rotation. Okay, so what are the puzzles of the deep solar dynamo? One is, why is it 11 years? The other is, can some of the properties of the solar dynamo be applied to other stars? And the other properties are like what role does the tachocline play? Do we have rising buoyant flux tubes from the deep convective interior? Is there some role that the surface flux plays? And there's all sorts of models that play with different aspects of these. Some other unknowns are what is the actual state and structure of the internal solar convection? So we can see pretty well what's going on at the photosphere, but what happens in the interior in terms of Rossby number of the convection is relatively unknown. So as far as modeling goes, how should we actually, one of the topics that I'll come to is how should we actually model these flows in a global scale where we can't resolve all the scales of convection and magnetism that the sun has, especially for emitting things like the surface. And furthermore, if there are unresolved features that are important at the surface in the tachocline, is there some way that these can be parametrized and included in global scale models? Okay, so the basic aspects for generating magnetic fields within the solar convection zone are, we have the omega effect. So this is where you have the differential rotation stretching out poloidal field and turning it into toroidal field. We also have things from convection acting on these magnetic structures, basically turbulent correlations of the velocity field and the magnetic field, which lead to something like the alpha effect. There are many ways of getting at these terms, particularly these terms. You can, say, run a big global scale model like Hideyuki does and I do and Matthias does, where you actually resolve these terms. Of course, you can do things like flux transport models, where you have something like a Babcock-Layton mechanism, or you can do something like mean field theory, where these things are parametrized based upon some turbulence theory in terms of closures for those terms. What I'll be talking about today is an ASH simulation. So ASH is the anelastic spherical harmonic code. It's a massively parallel pseudospectral code. It uses spherical harmonics to resolve horizontal structures, and in the case I'll be talking about, it uses finite differences to resolve radial structures. So this is the full spherical shell geometry. In this case, as you'll see, there's no tachocline. It omits some of the surface layers. So, of course, there's nothing like ionization or radiative transfer going on up in the upper layers, and there's no possibility of a tachocline. So the ASH code uses semi-implicit time stepping, which means you can overstep things like the sound speed or the fast magnetosonic waves. It also has a self-consistent evolution of the flows, magnetic fields, and the thermodynamics, at least in a linearized sense. Okay, so over the last basically 10 years, we've seen a kind of an explosion in terms of convective dynamo models. Some of the first ones, as far as these big 3D simulations go, and we could always go back to Peter Gilman's work from the 80s, or even earlier, where some of these features were captured. But basically, once the ASH code was built, we could do these higher resolution simulations where they're basically equivalent to 256 cubed or 512 cubed sort of simulations. We could start exploring parameter space in terms of the Navier-Stokes MHD equations. One of the first simulations that was done with the ASH code, at least, is this code. It was this simulation from Sascha Brunn back in 2004 when he first implemented MHD into ASH. And in this case, we were, because we wanted to have kind of small-scale fields and see what happens with a high magnetic Reynolds number, we're using larger magnetic Prandtl numbers, in this case of 4. And later, about 2 years later, Matt Browning ran one of the first tachocline sort of simulations, and that had a magnetic Prandtl number of 8. So what you'd expect in these is a small-scale dynamo, fast growth, and small-scale fields. Then Ben Brand came around and started playing around with these things back, I think, around 2007, but didn't publish this until about 2010, 2009, in which case he was looking at lower magnetic Prandtl numbers, in which case you should expect larger scale magnetic features to emerge. And what he found was that indeed you do get these wreaths, so large scale structures at low latitudes, that in this case they're not reversing, but they do have modulation in time, and this modulation in time is linked to the modulation of the differential rotation. Beyond Gazzaro and Company, which is this case here, where you have regular cycles, we did get regular cycles with ASH starting around 2010, and unfortunately they're quite irregular in terms of both the polarity reversal time scale, but also in terms of hemispheric symmetries. And in this case, what he's done is taken a solar-like simulation, so convection zone only. This generates wreaths, still these large axisymmetric structures. But what he's done relative to this case, they're both at a magnetic Prandtl number of 0.5, but he's spun it up from 3 times solar to 5 times solar, which reduces the Rossby number of the convection. In this case, it's much more cylindrical differential rotation profile and a much stronger differential rotation at that. Okay, so Guizzaro and company in 2010 published a very nice paper on a simulation with the OILAG code. It's a relatively low resolution simulation using numerics similar to ASH in the sense that you have an anelastic code. Some of the subgrid scale or unresolved motions are parameterized. But in this case, they also have a tachocline. And they also use something that's similar to slope-limited diffusion, wherein they implicitly reduce the diffusivities or dissipation in the code. And what they found was a long-running cycle of about 80 years, a polarity cycle of 80 years, and a magnetic energy cycle of 40 years. They even have some, depending on the color table you use, hints of equatorward propagation. And if we turn to the well-known paper, especially here, from Nick Nelson in 2013, there's actually one a little earlier than that, using ASH and something called dynamic Smagorinsky, which is another scheme for parameterizing subgrid scale motions, he was able to achieve something that had been long sought, and that is buoyant structures in a convection zone. In this case, it is also without a tachocline. So what happens here is you have strong fields that develop at the base of the convection zone, and eventually, in certain regions, they become strong enough to buoyantly rise throughout the bulk of the convection zone. Okay, so equatorward propagation is an important feature for the solar dynamo. One of the first simulations to really capture this robustly was done by Capilla Petra in 2011, and it continued in 2013 with a more recent AFJ paper. What they find is that they get equatorward propagation under some certain circumstances. In this case, they're actually running fairly high magnetic Prandtl numbers, but the circumstances are that you have a fairly large density contrast across your convection zone. Large here is relative, of course. The sun, it's like 14 density scale heights. These are more like 3 or 4. So if you do a systematic study and you go from something that's like Boussin-esque, so n rho of 0 to n rho of 3, you can systematically see that as you increase n rho, you can achieve more and more equatorward propagation-like features, as well as these polar branches. And they also, in a recent work by Warnecke, Jörn Warnecke in 2014, he showed that you can basically have a Parker-Yoshimura-like mechanism working here. So that is where you have the toroidal production is succeeding the poloidal production in a dynamo wave, at least in kinematic theory. Okay, so we've seen kind of an overview of what's happened over the last 10 years. I'm going to talk about a case that I ran for my thesis work actually back in 2013 and finally gotten around to publishing just last year. In this case, it's very similar to the others, where it's a convection zone only simulation. In this case, we're rotating at 3 times the solar rate in order to reduce the Rossby number of the system. But it does exhibit some really interesting features. One of those is this regular magnetic energy cycle, or you could maybe consider that something like an activity cycle, regular polarity reversals, equatorward propagation of magnetic features like this, and it also has a period of disrupted cycles and reduced magnetic energy that we're calling a grand minimum. Okay, so how is this problem really set up? So now you can actually see the depth of the domain. We go from about 0.71 to 0.965 or so, capturing a background state from model S in this case. You can see the diffusivity profiles for entropy, so that's kappa here, decreases as you go in as 1 over rho to the 1/2, and eta similarly drops as rho to the minus 1/2. What you don't see here is nu, right? So in this case, and I'll talk about this in just a second, we're using something called slope-limited diffusion to reduce the viscosity and viscous dissipation in the system, but only acting on the velocity field. On the right panel, you can see energy fluxes in the system, multiplied by 4 pi r squared to make them like luminosities. So you have the sum of all these things at 2 different times. You have the radiative luminosity that you expect from the solar model, so that is very close to 1 near the bottom. It's a little, I did this a little bit above the tachocline, so it's not perfectly 1. You have an unresolved flux, which is basically the L equals 0 component of the entropy diffusion. You have an enthalpy flux, so this is the energy carried by the convection. And down here we have small fluxes related to kinetic energy, magnetic energy, so basically Poynting fluxes, and viscous fluxes from the slope-limited diffusion. What we can see is that you have these dashed lines and solid lines. Those correspond to two different times. At magnetic maximum, that's in solid, and magnetic minimum is in dashed lines. So as we saw in a recent talk by Jean-François Cosset, is you can see modulation in the amplitude of both the convection, but moreover in the enthalpy fluxes related to the magnetic fields having an important interaction with the convection. So at magnetic maximum, you have a reduced flux because you've reduced the amplitude of the convection, and at magnetic minimum, the amplitude of the magnetic fields is reduced, and hence you have a larger convective flux, larger convective amplitudes. Okay, so slope-limited diffusion. This is an important component of this model, and basically how it works is you perform a reconstruction in each cell. So right now we're just looking in one direction. This is done in all 3 directions for the velocity field. So the idea is that you take the cell center value, which is this Q sub I here, and you perform a reconstruction to a cell edge. And you can do this many ways. For instance, you could have an nth order scheme where you reconstruct many values of the derivatives, say the first order derivative, second order derivative, and you can do higher and higher order corrections to this. It becomes increasingly complicated to maintain monotonicity of these various derivatives. Here, because we're only using this as a diffusion, I use only the first order derivatives. This is very similar to the scheme that Matthias has, Hideyuki has, and Yuhong has as well. So the idea is that you have some speed, diffusion speed. Yes? You bet. Yeah. Not 50%. Yeah, yeah. As I'll show you also, the differential rotation is significantly modulated by about the same amount. Yeah. Yeah. Very different beast than the sun. But it still has some interesting features that might be related. Yes, Yuhong?
I just have a question also about, yeah, so this direction of the range between maximum and is opposite to what right?
Is it? So I think it's the same as theirs. When at maximum, I think they have less transport. Yeah. Are you sure? I think it was reversed.
I thought they were consistent with the
Uh-huh.
So at maximum we have. Well, I thought that.
Okay. So this is reversed to them then. Interesting. Okay, thank you. Okay, back to the slope-limited diffusion. So to construct a diffusion, basically you need to figure out a flux of a certain quantity across a cell edge. And you do this by multiplying the difference at the cell edge, which is from this reconstructed value, by the speed at that cell edge. The other piece that I didn't talk about. So here, when you're reconstructing this slope, what you do is you say, okay, we have the actual value of the derivative, which is computed with whatever scheme you have for your numerical scheme. So in this case for ASH, we have spectral derivatives in the horizontal and fourth order derivatives in the vertical. And then you apply a limiter, or is that right? Yes, you apply a limiter to one of the values and reconstruct this, this derivative at cell center. And that's done with this limiting function here, where you take the ratio of the reconstructed derivative to the actual derivative. And this complicated form is just showing you that you have, with all the geometric corrections for spherical geometry, you can compute what the change in a given quantity should be with time. So it's basically just that's your diffusion operator. And then to account for changes in energy, you compute the slope-limited value of the kinetic energy in this case and the change in momentum. That gives you a change in the entropy. Okay, so to kind of make contact with some previous simulations, both from ASH, from OILEG, and the pencil code, it's useful to try and understand what some of these effective parameters are given the slope-limited scheme. So under a few simplifying assumptions, namely that we only take the first derivative, so you drop some of the higher order terms, which can be antidiffusive, and look at only a constant cellage speed, you can construct an estimated value for what the diffusion coefficient should be. So here you have effectively your filtered Laplacian and your full Laplacian, and their difference gives you what the slope-limited diffusion operator is roughly acting like with relatively smooth fields. So in this case, the AD is just the area of the downflows, and A is the total area. So taking the ratio of those two things gives you an effective viscosity multiplied by this diffusion speed and the grid spacing. So this is, of course, much like OILEG and other slope-limited diffusions, you have a grid-dependent diffusion. So if using the basic values from this simulation, namely the amount of area covered by downflows divided by the total area and an average delta x, you can reconstruct what nu effective is, and it's roughly about 5 times lower than what you can nominally resolve with a Newtonian diffusion. So in this case, the effective Reynolds number near the upper boundary where this diffusion is largest is about 350. But the important numbers to look at relative to other cases is this is a relatively low thermal Prandtl number, it's about 1/10, and a relatively low magnetic Prandtl number, 1/4. Okay, so what does the convection look like in this thing? Here we're looking near the surface where you have fairly small granules as you'd expect as you get closer to an upper boundary. So upflows are in light tones, downflows are in dark tones. And you do see some alignment of features with the rotation axis. As you go down in depth, you have increasingly Taylor-like column structures, which are these elongated north-south structures. And they become more homogeneous because your density contrast, your local density scale height is becoming larger and larger. Similarly, as you increasingly go deeper into the simulation, you have larger and larger scale flows, and you do maintain this alignment, which basically is saying that you have a larger Taylor number or a low Rossby number in those regions. Okay, so these convective flows, along with the thermal wind balance that they establish a differential rotation. In this case, it's somewhat solar-like in the sense that you have slower poles and a fast equator, but it's cylindrical rather than conical. And the largest reason for that is that it doesn't have a tachocline. So it can't build up a thermal layer here that would support those conical contours. Although in some regions it does have a relatively flat radial profile. So it's somewhat similar to the sun. And you can also see in some regions you have something that kind of looks like a near-surface shear layer. Namely, you have a decrease with angular velocity as you go closer to the upper boundary. Okay, so I mentioned that the differential rotation and the convection are modulated by, along with the cycle. So in this case, you're seeing the differential rotation energy in black. So this is just averaged over the entire volume. You have kinetic energy in the convection in blue, toroidal magnetic energy in green, fluctuating magnetic energy in red, and poloidal magnetic energy in orange. So you can see that toroidal magnetic field is much larger than the poloidal field by about a factor of 3 or 10 in energy. Moreover, you can have these very large changes in the differential rotation. So in this case, this corresponds to roughly 50% modulation of the differential rotation. You can also have these significant excursions in the convective kinetic energy related to that modulation that I showed you in the luminosities of the enthalpy flux. And if you look in detail over a range of cycles, in this case, sorry, I lost my time axis there. This is over about 22 years. You can see where that modulation occurs. So you see a significant modulation, particularly at low latitudes of the differential rotation. You have something that looks kind of like torsional oscillations at higher latitudes. All right, so what you're seeing here is the toroidal magnetic field. So field pointing against longitude is in blue, and prograde is in light tones. And we're going to march through just a couple of cycles so you can see what the average kind of behavior is during these fairly regular cycles. In this case, what you're doing is you're building large-scale, fairly axisymmetric structures on the edges near the tangent cylinder, so where the gradient, the shear gradient in the differential rotation is largest. As the cycle proceeds, this moves to increasingly low latitudes as the local differential rotation is reduced. You also get these polar caps that are related to the spin up of the polar regions, which you saw in those torsional oscillations. And then as you reach a magnetic minimum, because the reeds are becoming so close, you have a lot of cross-equatorial flux. This allows for the cancellation of the reeds and then an eventual dispersion of a new polarity of both toroidal and poloidal fields. Okay, so just to walk you through a single cycle. So this is between years 24 and 31. So I'll get to that a little later, but the basic reason is as the reeds approach the equator, you have these kind of Taylor column structures. So you start magnetically linking the two reeds significantly with those elongated north-south structures, which allows flux transport across the equator. The other component is dissipative. You have a magnetic diffusion, and as they approach, the magnetic diffusion becomes large. You have a fairly strong gradient in the magnetic field there. Right, you go from negative to positive. So those two mechanisms are primary means of creating a large cross-equatorial flux. Okay, so on the top, we're looking at this time-latitude diagram of longitudinal magnetic field, azimuthal magnetic field. We've just picked out a couple of times. So this one's near magnetic maximum, this is near magnetic minimum, and we go back towards the maximum. So you can see here the convective patterns near the top of the domain. So this is at 0.9 solar radii. The flows are about 100 meters per second or so fairly strong, which means the Rossby number is of order of about 0.5. You can see the polar spin-up, which occurs primarily near the upper and lower boundaries. You have a strong prograde differential rotation at low latitudes. And if we look at what the fields look like at this time, you have a strong polar cap, these low latitude reeds that are forming near the tangent cylinder, and they, of course, have opposite polarities. The peak magnetic field strengths are of the order of about 40 kilogauss or so near the base of the convection zone. Okay, as we go towards the time where these things start to migrate towards, as these low latitude reeds start to migrate towards the equator, you can start to see this disruption of the convection at particularly low latitudes. This disruption of the convection is what leads to that modulation in the enthalpy flux. Now we've also wiped out those polar caps in terms of their torsional oscillations, so now we have a very solar-like differential rotation with slow poles and fast equator. You can see the reeds strengthen as well, become more axisymmetric as we reach this period in time. Okay, so now we've actually lost our reeds for the most part, and we've achieved a more non-axisymmetric magnetic state, and we've also seen the convection recover. So go back just one, you can see this disruption here, convection recovers and is more north-south aligned. Okay, as we move into the minimum, because the convection's kind of reasserted itself, you now have a spin-up of the poles, and also are starting to form this new opposite polarity. We've gone through a reversal, so now you're starting to form this new opposite polarity wreath structures. As we move close to the next maximum, you can see that the poles have been spun up, and as the cycle proceeds, those will spin down again, and you're starting to see the influence of the convective the wreaths on the convection again. Okay, so one thing we can do is look at an average polarity cycle. So this again are the volume averaged magnetic and kinetic energy densities. So black is DRE, the differential rotation kinetic energy, and blue is convective kinetic energy. And what you can see is, of course, unlike the previous plot where I showed you where you have those really deep minima, the average cycle doesn't quite have that. But the features that you saw in those average cycles are basically repeated here, namely have this Equatorward propagation of toroidal magnetic field and a poleward branch as well. Okay, so what you're seeing here is the volume integrated magnetic energy generation rates. And what I want to point out is that here you see the mean shearing term, so this is basically the omega effect, which is here. And it is modulated significantly with the cycle, changing by about a factor of 10. And the reason for that is, of course, well, you're modifying your differential rotation. And what you're seeing here is the gradient of omega, magnitude of the gradient of omega, at 0.9 solar radii. So you can see that this follows and is very closely correlated with the magnetic field. So this is an evidence of the Lorentz force feedback on the differential rotation, and hence kind of this quenching of the mean shearing terms. The other piece to this, of course, is that it's not just the mean shearing terms that are wiping out the differential rotation. Instead, you also have a modulation of the Reynolds stresses. And this modulation of the Reynolds stresses, of course, happens because you've changed the structure of your convection, as you saw in one of the previous images. So as the cycle proceeds, the magnetic fields strengthen, and it weakens the Reynolds stresses that tend to maintain the differential rotation. Okay, so one interesting thing to try with this is, can we characterize this dynamo in terms of mean field theory? So what you're seeing here are the 9 components of the symmetric, so 6 components of the symmetric alpha tensor, and the 3 components of the turbulent pumping vector. So what I've done here is you take a long time sequence of data from the simulation, and you perform an SVD composition similar to what Racine and company did in 2011. This SVD composition gives you a local value for what the alpha tensor should be given. You make a few assumptions, namely that everything's delta correlated. Some of the primary features are, of course, that you have this north-south asymmetry, but you also have a radial asymmetry between the top and the bottom of the convection zone, which is related to the change in the sign of the kinetic helicity. And what we can do then is also compare to previous simulations. So on the left, we have those 9 components of the alpha tensor from Racine, the 9 components from this simulation, and then one from a simulation called D3B, which was Nick Nelson's published work in 2013. And you can see a lot of similarities between these. Some of the differences arise because the Euler code uses colatitude versus latitude, or vice versa. Rather, they use latitude and we use colatitude. So that will flip the sign of north-south. But you see a lot of the same features in the sense that you have this reversal in radial symmetry as well as this north-south asymmetry for certain terms. But the important, to actually get this, to actually characterize this dynamo, what you need to do is take the ratio of various terms. So here we have the alpha effect generating poloidal field, and we have the mean shearing term. So this gives you an idea of how important the alpha effect is relative to the omega effect. In this case, it's only about 1/10, 8%. But that doesn't tell you the entire story. What you need to do is actually look at the ratio of the poloidal alpha effect to the toroidal alpha effect. For instance, if this was an alpha squared dynamo, you'd expect these 2 terms to be roughly equal in magnitude, but they're not. They're different by about a factor of 5, 4.5. Which means that this is really an alpha omega dynamo, which is in large contrast to most other convective stellar dynamos where they're more like the alpha squared kind of mechanism. So these 2 guys are almost equal players. Okay, and the reason that I have actually gone through all this analysis is to make an assessment of why do we have Equator propagation in this simulation. So I mentioned Capilla's work as well as Jeroen Warneke's work, where they've shown that, oh yeah, okay, we can see a Parker-Yoshi mirror mechanism. So basically this is a classical linear dynamo wave that has a propagation velocity like this. So it's proportional to alpha, the scalar alpha effect, and gradients in omega. The classical scalar alpha effect only includes kinetic helicity terms. So that's this v prime dot omega prime. And if you use this term only, as far as I know, Warneke's work does not work. And it does not work in this case. What you also need is the current helicity. This can, in principle, change the sign of alpha, which will allow you to have the correct propagation direction. So let's look at that. So first, we have the classical Parker-Yoshi mirror mechanism using only the kinetic helicity. And in this case, you see that the mechanism cannot work. Namely, the propagation direction is opposite of what you'd want it to be. So in this case, it's poleward at low latitudes and equatorward at high latitudes. So classical Parker-Yoshi mirror mechanism does not explain the equatorward propagation in this case. Now let's say, okay, we want to include the effects of the kinetic helicity, and we can do that self-consistently by using the phi-phi component of the symmetric alpha tensor. So replacing the scalar alpha here with alpha phi-phi. In this case, it will include both the effects of the kinetic helicity and the current helicity. And yet this mechanism still does not work, particularly at higher in the convection zone. There is some hint that it could work at lower latitudes. However, the clearer picture is that just because you have these changes in gradients of omega, you've changed your omega effect, which means that you're basically wiping out the local shear with these magnetic structures, both by suppressing the convection, which generates the differential rotation, but also locally draining energy from that kinetic energy reservoir, the differential rotation. You could say, well, maybe it's the meridional circulation. However, the meridional circulation is of the opposite sign of what you need to get it to propagate towards the equator. And basically, this is just a gyroscopic response to the changes in the differential rotation arising from Maxwell stresses. Okay, so basic idea is that equator propagation arises from Lorentz force feedbacks, period. Okay, so now we can look at why does this thing reverse, and how does it reverse? So what you're seeing here are changes in the poloidal vector, vector potential. So this is the phi component of the poloidal vector potential. Here it is at one point in time. So this is, you take the maximum of the beginning cycle and you average that over all the cycles. And here you have the succeeding magnetic energy peak averaged over all the cycles. And you take their difference. And the idea is that, this is I think first done in Nick Nelson's paper in 2013, the idea is that you take the time integral of the various components of the right-hand side. In this case, you have the mean EMF, the fluctuating EMF, and magnetic diffusion. And the idea is that all three of these terms should cancel to give you something that looks like this term here. So if you compare delta A phi to the right-hand side, so that's the sum of these three terms, you see that they're quite close. So things are adding up there. Now we can ask, which is the dominant component? And in this case, it's really just a competition between the fluctuating EMF and resistive diffusion, with some potential components arising from the near surface regions at higher latitudes. So that's these red things here contributing to this. So while there's not a clear component that is dominating here, what we can do is, okay, let's look at a time evolution of over a single cycle. So this is B phi, and you're looking at the azimuthal average of the toroidal magnetic field, and then also the phi component of the vector potential, which captures the poloidal field. So as the cycle proceeds, you can see these wreaths grow, and at low latitudes, we kind of missed it, I'll wait for it to come around again. You can see the formation of a low latitude EMF that leads to a change in the sign of A phi. And it's starting right here. So it starts near the base of the convection zone and then eventually spreads to the rest of the domain. You get a large-scale topological reconnection of the poloidal field that originates at low latitudes near the base of the convection zone, spreads towards the upper boundary, and then quickly spreads to the rest of the domain. This occurs roughly over an Alfvén timescale. Okay. So what you're seeing here are two components of or two magnetic helicities. So this is the volume averaged in a hemisphere magnetic helicity, so A dot B. And here you have the current helicity, or B dot J. And you can see very clearly near reversals you have this change in the sign of the helicity between the two hemispheres, both in the magnetic helicity as well as the current helicity. In contrast, at deeper in the convection zone, so near the lower boundary, you don't really have this reversal in the magnetic helicity, which is quite interesting. But you do still have a reversal in the current helicity. Mark Misha and I actually have a project going right now to look at what the role of helicity transport across the equator, so this is that cross-equatorial flux mechanism that I was talking about, plays in this dynamo and other dynamos as well. Basically trying to construct a gauge-independent helicity transport. Okay, so finally, one of the promised features of this dynamo was that it has a grand minimum. So to give you an idea of how much the magnetic energy changes relative to the normal cycles, you can look at the dotted black line here. And that dotted black line, you could say maybe it changes a little bit. And the reason for this is that really you get large excursions only at lower latitudes. And that magnetic energy changes by about a factor of 2.5. So the grand minimum really occurs near, the basic features of the grand minimum occur at lower latitudes rather than the higher latitudes. But what you can see relative to previous cycles is that you have this loss of the prominent polarity cycle. So here, you lose your heartbeat. And you have these large excursions of flux across the equator. So we can ask what initiates these? And it seems that, it's not conclusive proof, but it seems that you have a hemispheric asymmetry. In particular, you have a hemispheric asymmetry in the non-axis symmetric modes. So this is, what you're seeing here is the sum of all the modes from L equals 0 to L max, but summed only for m's greater than 1. And you're seeing this near the surface here and at depth here. So the two features that I've highlighted here and here are these regions where you have this large hemispheric asymmetry. In particular, this feature here has a strong signal during what should normally be a magnetic minimum. And similarly here, as you exit the minimum, you have a similar feature, but in the opposite hemisphere. At depth, the signal's not quite as clear. I should also mention, of course, you have this big gaping hole during the minimum, so lower magnetic energy state at low latitudes, whereas you do keep your fairly regular magnetic energy cycles at the pole. Deeper in the convection zone, you have a similar feature wherein you have a hemispheric asymmetry, although it's not nearly as pronounced as it is near the top of the domain. Okay, so if we look at the axisymmetric modes, what's happening there? We can split the axisymmetric modes into two pieces, the odd and the even modes. So thinking here, you just put m equal to 0. And if you look at the odd modes, so these would give you your hemispheric antisymmetry that you typically see. So positive in the north, negative in the south. And you can see during regular cycles, it's quite large. But during the minimum, and in particular at depth, the amount of energy in the odd modes is significantly reduced. And yet it increases slowly as you move out of this period of disrupted cycles of this grand minimum. In contrast, for the even modes, you have an excitement of those even modes, particularly at this point, which is where you have that large hemispheric asymmetry in the non-axis symmetric modes. So you excite a strong even mode as you're entering a strong even mode in the axisymmetric modes. as you're entering the grand minimum, and those modes decay away, particularly at depth, as you move through the grand minimum. One way to kind of characterize this, we can say, what is the average parity of the dynamo? And that is that, particularly near the surface, it's quite antisymmetric during normal cycles, and even during the grand minimum, there are periods where it's fairly antisymmetric, and that the average parity for fields near the radial fields near the surface is about minus 0.9, whereas at depth it's not quite as antisymmetric. In fact, it's more like about minus 0.7 for the typical parity. But what you do see is that during the grand minimum, you have this excitement of a near even, or I shouldn't say even, near neutral parity. So this would, this is suggestive, as you can see here, that you're exciting both dynamo families, the antisymmetric and symmetric dynamo modes, or the primary and secondary families in the nomenclature of De Rosa et al. 2012. I should say here that, since I have a few minutes, one of the possible reasons that we can get into such a state, this intermittent or aperiodic state, is that we have a fairly low magnetic Prandtl number. It was seen with mean field theory, and particularly those with the Malkus-Proctor effect. You can get into states where, with a low enough Prandtl number, you can have this kind of intermittency. This is shown by Moss 2001 and Brook 2002, wherein they explore a magnetic Prandtl number space of about, I think, 2 orders of magnitude. And they show with lower magnetic Prandtl number, say about a tenth or so, you can start to get to these highly aperiodic states. Okay, so just back to the basic features of this model. You have regular magnetic energy cycles, regular polarity reversals, equatorward propagation of structures, poleward migration of features, something that's kind of like a grand minimum. And I will leave it there.
Questions for Kyle?
Yuki? Yeah.
So I'm interested in the comparison between yours and the Capilla's calculation. So I think the significant difference is magnetic Prandtl number.
Yes, they are typically running at high magnetic Prandtl numbers.
Okay.
So between 4 and 10.
So in your case, so you are using a lower magnetic Prandtl number, and you can get a significant feedback to the differential rotation.
That's right.
But in my thing, this is a bit counterintuitive because lower magnetic Prandtl number means higher magnetic diffusivity compared to turbulent viscosity.
That's right.
But so this indicates a smaller magnetic energy. But in your case, the feedback is stronger. So do you have any comment on this thing?
So the reason the feedback is so strong is that it changes the low latitude structure of the convection. So you have this nonlinear feedback on the Reynolds stresses, or the lambda effect. This is the primary reason that you can have this, this kind of feature, this modulation in the differential rotation that's so extreme relative to other cases, despite having a relatively low magnetic energy.
Oh, okay.
Yeah. Although, I mean, at times the magnetic energy is roughly in equipartition with the convective kinetic energy, at least near magnetic maximum.
Can't resist pointing out the irony that these enormous calculations that all the groups have done, when they come to interpret their results, what happens? They fall back on mean field concepts. And so in some sense, what you've got is an extremely expensive mean field
theory calculation. Yeah, in some ways, yeah.
But my question would be, this clearly isn't the sun. Is there any known star with a faster rotation that has cycles that shows these large variations in luminosity or differential rotation?
As far as the differential rotation, yes. You could look maybe at Tau Buddhis. Travis might have a better answer for this than I do. But Tau Buddhis does show some modulation in the differential rotation.
What about luminosity?
That I don't know. I don't know.
I mean, it would be obvious from the data.
Oh, yeah.
The magnitude you're talking about.
That's right, yeah. I don't know off the top of my head.
Now, this feature that you identified as a grand minimum, if you I mean, if I remember correctly, the Maunder minimum, while there were hardly any sunspots, we now know out of C14 and beryllium data that there was a cycle and that the phase wasn't lost.
Right.
Are you losing the phase?
So only at low latitudes. The phase is still kept at the high latitudes. You see this strong modulation. So it keeps its cycle period. What it loses, and this is in contrast to the sun, is that low latitude polarity cycle.
So, I mean, it could then be that this is something entirely different.
Yes.
Than the Maunder minimum. And my second question, if I may, is your slope-limited diffusion, would your physics judgment be that it overemphasizes then the magnetic losses?
No, I don't think it overemphasizes magnetic losses. The slope-limited I don't think it overemphasizes magnetic losses. The slope-limited diffusion here is acting only on the velocity field. So relative to other cases, it's not that different.
Zeeman Doppler imaging of some relatively rapidly rotating stars is now able to resolve medium scale structure of magnetic field.
Right.
Have you seen any evidence of these banana cells or anything else in any of those new observations?
Ooh, banana cells, that would be tricky, I think. Maybe active magnetic longitudes. But evidence for banana cells I'd be pretty skeptical of.
And the question about that Peter raised about the luminosity, as I understood it, the total luminosity wasn't changing. It was just being partitioned in different ways.
That's right. That's right.
And so that's not observable.
The flux out the top was the same. Yeah. I'll show you. Let's see if I can get back there quickly. So what was being modulated was the internal fluxes. It's a faster way. So the flux at the boundary is fixed just by the boundary conditions. Yes, it is a simulation. Yeah. What's changing, as you pointed out, is the convective flux, but that drops to 0 near the upper boundary because radial velocities go to 0. Oh yeah, oh yeah. This is not the sun.
I mean, one more comment on the luminosity issue. I mean, what really matters for the photosphere is what is the entropy of upflow regions. The photosphere doesn't really care what is the convective energy flux somewhere beneath. So as long that can fluctuate, but if you don't change the entropy of upflow regions, that doesn't necessarily lead to an observable luminosity change.
And that's what we see here.
But it's hard to really look at if you only have a photosphere in your simulation.
Yes, of course. But what I can say is about the entropy. The entropy fluctuations don't really change. So you wouldn't see it in the photosphere. What does change is the convective amplitude, which is why you have this modulation.
So what is changing the entropy flux?
The enthalpy flux is changing, and it's changing because VR is changing. Yes, Michael.
The actual magnitude, not just the actual magnitude of VR, not just the correlations.
That's right.
Okay.
That's right. Yeah. Both change.
So, I mean, I fully acknowledge the value of trying to simulate with the machine that you now have other realizations of stellar dynamos and then have maybe more obvious comparison cases with other stars. But I would like to ask the question, because you kind of cherry-picked in the simulation what features sort of coincide with some of the aspects of the solar realization of of a dynamo, what other observations on the sun with the simulations having been evolved to the state where they are now would help to further constrain that you don't have?
So an observational constraint that we don't have is effectively the Rossby number of the interior. One observational constraint that we don't have that's well pinned down is what the Rossby number of the interior of the sun is. Like I mentioned in the...
How would you measure that?
Well, helioseismically nominally, right? You could do some sort of measurement to try to figure out what the at least peak amplitude of the convective structures is in the interior. Kind of like, I think there's a paper that Reiner, Mark Misch, and I think it was Nick Featherstone was on that paper as well, where they looked at kind of what, theoretically, what should be the lower bound on the convective amplitudes is. And if you look at the observations, they say, okay, well, maybe it's of the order of centimeters per second or something, in which case your Rossby number would be tiny, like 10 to the minus 4, 10 to the minus 5. But if you take the more realistic values that you can constrain by gyroscopic pumping, it's more like 10 to the minus 2 to 10 to the minus 3. But that's still a fairly large range.
And what do you mean by realistic?
In terms of the gyroscopic pumping?
Yeah.
So basically, it's consistent with what you see for the observed meridional circulation as well as the observed differential rotation. It's still at least 2 orders of magnitude less, yeah. But getting to those states is very hard with these low-resolution models. You can do it with high-resolution models, but you can't run them for a century. At least not yet.
So can one then quantify what kind of a resolution and accuracy is needed for helioseismology to really be discriminative?
I think so, and it's probably not achievable.
And how far away from those quantities we are? I mean, shouldn't that be the question?
Well,
then in any design for the next seismology instrument.
I think so, yeah. I'd love to see that data.
Okay. More questions? Let's thank Kyle again. Thank you.
Thank you all.